Anyway, so now we're to the most exciting part in my view is like now we're getting the real-time PCR, which we could think of like the let's see whether what we got made some sense or not. And so we were given 3 different data coming in 3 different normalizations, and we don't know exactly which one to use. So this is an interesting thing because this is something you could find in a machine learning textbook. So the red line is what is called the learning curve. When on the x-axis you have on the x-axis you have the tuning parameter, which effectively controls overfit. Overfit meaning that when you see 0 here, it means that you got perfect separation. So those real-time PCRs were very good in dividing cerebrum for cerebellum patients, but the problem is not in prediction, but looking at the labels. Okay, so it's like the easy thing, right? So I see guys on this side, guys on the other side. I draw a line. So, but that was not the goal. So, what statisticians or machine learning people know is that, well, this is that you have to turn your knob and find a solution which is a little less complicated than the one you selected. And so we know that once we start turning the knob, we will start making some mistakes. And so there will be some errors. And now this is the prediction curve. So what we do, we keep some data on the side. And we check, well, for this value of the parameters, what is our prediction ability? And when you see this gap, you know that you are overfitting. So you're in love with your data, so to speak, right? So, or it's too easy to predict when you know the truth, right? And it's not that easy in real life. So you turn the knob, and ideally, what you should find is that the blue curve at some point starts bending down and narrowing the gap with the red line. Right? And this means is a good sign, so to speak, because it means that now your prediction is close to your ability of separating the 2 subtypes, and then you can be sort of more relaxed about the fact that in the future those will be your prediction ability, so to speak. And now the 3 plots we have, the one on the top on the left was definitely the one more promising. What we got here is actually the average of five runs, but I mean this seems to be going in the right direction. And incidentally, this tells you that around here there will be an average of 5 different guys, but around here we will select the value of the parameter we're going to use to try out our system. And so the way it goes is that, well, now we decided to use that particular normalization, which is the delta CT, right? Normalization, the first one. Using that normalization, this is each of these circle is the value of a function f of x. You remember, we computed the beta coefficients. Now the x vector is a bunch of real-time PCR figures. We add them up, weighting them with the beta values, and we get the function f of x. And now we never do something particularly intelligent, so now we simply check whether it's positive or negative, right? So if it's positive, it's type 1. If it's negative, it's type 2. So now what you see in blue is good news. I mean, the test is correct. Of course, we hide the label first, and then we check, and there is no leak in the procedure. Now, what you see in red is what is missed by the real-time PCR. What you see in green, what were the original errors we made, and what you see in blue, and so whatever is blue and green, it means that now is correctly classified, but previously was incorrectly classified. Right. So I think the interesting bit is that the prediction ability of the real-time PCR is slightly better actually than with the microarray, but is in the same ballpark, I would say. So I wouldn't be too picky, just 1 against 2. So it's just, these figures are to the limit of statistical significance, but they are, I would say, safely below chance, right? So the two sets in this case are almost 50% apiece. And so it's an interesting result, and is in line with what we were expecting. What I like is that if I go to the heat map, so I don't want to use bad words. I mean, it doesn't seem too good, right? It doesn't seem too promising. And if you look at the histograms of a single gene with the normalization we used, is not exactly exciting from the viewpoint of what is overexpressed or underexpressed, right? And what we learn is that actually the analysis done by the Gaslini team, I mean, using a different normalization depending on the subtypes could actually be very helpful, maybe changing also the normalization, right? So there are a bunch of different issues here. But from our viewpoint, this is, at the same time, is also, I think we're going to use this as, we feel we could use this also as a way of validating what we are doing. Or let me put it this way. I think at the moment we like to think that from the theoretical viewpoint we have our reasons to believe that what we are doing is interesting. And from the molecular biology viewpoint, this is definitely the most interesting, but it's not even, is already, I mean, we've been obtained over the last few years a few good news out of what we are doing. So this is again in line with what we were expecting. So we are very excited about it. And I'll skip that.